Welcome to lecture number 46 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have done in the previous lecture. So, in the previous lecture, we looked at linear elastic example, okay, for a nonlinear beam column element. If the material behaves linear elastically, we have proved that you need 2 Gauss-Legendre integration points or 3 Gauss-Lovato integration points at least to get the exact solution. Okay. And then we have studied strain hardening response using both displacement based element and force based element, and we showed that in force based element you can use only one element and increase the number of integration points to get the exact solution, whereas this cannot be done in one element with number of integration points. No matter how many you use for displacement based elements, you cannot get the exact solution, because it is in the assumption of the displacement based element where we assume that the curvature varies linearly along the length of the element and axial strain remain constant along the length of the element. However, if we use more number of displacement based elements, we can get exact solution. So, that is what we want to do in this lecture. And also we want to talk about the issues of displacement based and force based element, and that is called localization issues. What is it? And it happens for elastic perfectly plastic as well as for strain softening response. So, we will look at the elastic perfectly plastic response case today. Okay. So, let us continue with the strain hardening example, but this time we will use displacement based elements. Okay. So, now I want to use multiple displacement based elements of equal length. That means this cantilever is going to be modeled like this. So, let us say I have this cantilever of length 3 meters. So, I will now discretize it into many elements. Okay. So, each is a displacement based element of equal length. Okay. And then in each element I will be using 3 Gauss-Lovato integration point, which I am not changing. Okay. Everything else remain the same as before. So, this example is already shared with you. I will not get into the OpenSys file, but you can go there. The objective is to show the convergence of global and local responses with increasing number of elements. So, for displacement based element, if you increase the number of elements, you can get the converged solution. So, let me show you the axial force versus the vertical displacement response. So, this gray is the reference solution, which, as I discussed in the previous lecture, I obtained it using 16 force based elements, where each element has 5 integration points. Okay. So, this is very accurate. Okay. So, for 2, 4, 8 and 16 number of elements, this is how the response converge. Okay. As you can see, for 2 elements the maximum vertical displacement is this much, which is then converging, and you are getting the final solution. Okay. On the other hand, for the lateral force versus lateral displacement, okay, you can see this is for 2 elements, then the green is for 4, and then eventually it is converging, right. It is matching with the reference solution as you keep increasing the number of elements, right. These two are global response. What happens to the local response? Again, I am looking at the curvature at the integration points along the length of each element, and now my number of elements are varying. I have 2, 4, 8 and 16, and plotting them along the length of the element for curvature as well as for bending moment at the integration points or Gauss points or the cross section. They all mean the same thing. Okay. So, again along the length, right. What do you observe? Well, you see that here the curvature is small because at the top it is remaining pretty much linear elastic, right. All the yielding and inelasticity is happening at the base of the cantilever, right. So, this gray is my reference solution. Now, what you notice, let us consider the 2 element. 2 element means I am using, this is my 1 element and from here another element. So, you see that the curvature is varying linearly within the element, right. Similarly, let us consider the 4 element case. So, this is 1 element, then there is the next element and then the other one, right. So, within each you can see the curvature is varying linearly, and then there is a sudden jump. Okay. On the other hand, in the bending moment diagram, remember what I am plotting. I am plotting the bending moment at different sections. So, let us say I have used 2 elements here, okay, and then I have 3 integration points in each element. So, I am using Gauss-Lobato. So, this circle is integration points. So, I have 3 integration points for the bottom element, and then for the top element which I am drawing here, I have again the 3 integration points, right. So, these 2 integration points for the 2 elements case are at the same location, right. So, I am recording their bending moment at the section level, and you see for the top one it is here, for the bottom one it is here. And of course, the bending moment, as we have seen in the previous example, they do not vary linearly because my curvature varies linearly in a displacement based element, right. But as we keep increasing the number of elements, eventually I get the exact solution and it is linear. The bending moment diagram is linear. Okay? That is what I expect, because there is no load in between in this cantilever. There is no load between this point and that point. Okay? Why is this happening? Because if you recall the formulation, this is a manifestation of the weak equilibrium. What do I mean by weak equilibrium? We are satisfying the equilibrium in an integration sense. So, let me write it down. If you recall, the element end forces, my S, is equal to integration A transpose X, where A is the matrix of shape function, the displacement interpolation function, multiplied by S bar X dx, and this integration is performed using numerical technique. In this case, I am using Gauss-Lobato, 3-point Gauss-Lobato integration. Okay. So, because of this, right, just to remind you what is S bar? S bar contains, let me write, S bar X is Nx and Mx, the forces at the section level, and what is my S is equal to N, Mi and Mj, the axial force at the end of the element, the moment at end I and moment at end j in the simply supported basic or deformation coordinate system. Okay. So, because of this is I am calling a weak equilibrium condition. Okay. We are getting this problem, but if you keep increasing the number of elements, the result is matching, and so is the case for the global response. You can see lateral force versus lateral displacement. As you increase the number of elements, it is basically matching quite well. Okay. Now, for the axial strain, what happens? Just like the curvature varies linearly within an element in displacement based element, the axial strain remains constant. So, for example, for the 2 element case, this is the axial strain for the bottom element. For the 4 element case, the green one, this is at the bottommost element. Then you have like this, and the rest are very difficult to differentiate. Okay. So, the black one is for 16 element. You see, this is how the axial strain is varying along the length of the element. What is happening for the axial force? Again, like I said, the axial force is satisfied, both axial force and bending moment, in an integration sense. So, therefore, if you keep on increasing the number of element, eventually you get this. You add them, average out, okay, you will get this thing. Okay. So, that is because of the integration. So, that is what I am writing, which is manifestation of weak equilibrium. If you go to the example, I am also plotting the moment curvature response at the base of the cantilever and axial force and axial deformation response at the base of the cantilever. Okay. So, what we conclude from here, that the solution converges with increasing number of elements, but is it very efficient computationally? For example, let us say I have to model this multi-story building frame, right. So, I am just showing, for example, 2-story. Okay. Now, this is subjected to lateral load as well as gravity load. If I have to use displacement based element, I know here, 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 there will be inelastic deformation, right. So, I have to use many elements to model each beam and column. So, that will increase my degrees of freedom, okay, and that means consequently the computational effort will also increase. So, it is computationally efficient if I have to use displacement based element to do a finite discretization where we know the plastic hinges are supposed to form. That means where your element is undergoing inelastic deformation. For example, here, 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 I can do a finer discretization. Everywhere else, I can use longer elements, okay, and probably one element would be sufficient. So that is the idea for the next. So what I am saying, this is example 5, again shared with you, okay. So use multiple elements, but with smaller elements in plastic hinge region. So let's say I am saying that from here to here, this is my plastic hinge. So what I will do, I will use half the elements. Let's say if I am using 4 elements, so in this region from here to here, I will use 2 elements. So each element is like from here to here, these are 2 elements. Then for the rest, this is 1 element, this is another element, right. So for the case of 16 elements, in this region, I will be using 8 elements, and the rest will be modeled using 8 elements. This is just an example, okay. Does not mean that this is how you have to do it, but I am just trying to make some points, okay. The other thing, we will use Gauss-Lobato IP as before, 3 Gauss-Lobato, and everything else remains same as before. And again, we will show that the convergence of global and local response with increasing number of elements, okay. In the previous case, I discretized this with elements having the same length. Now I am saying I will do a finer discretization here at the base where plastic hinge is forming, and then a coarser discretization everywhere else. So now what do you see? 2 element is also giving you a very good result. 4 element is almost giving you a converged lateral force versus horizontal displacement response, okay. Because for the 4 elements, I have 2 small element at the base, and then the upper part we have the remaining 2 elements, okay. Let me show you the variation of the curvature along the element length, okay. So this is the case where I am using a finer mesh in the plastic hinge region, right. What do you see? See, basically this is my curvature distribution, the exact curvature distribution. Now, how do you capture this using element where the curvature varies linearly? So basically all I am trying to do is actually discretize this using straight line segment. So you need many elements to be able to do that, okay. But this part, it's fairly linear. So I can just go ahead and use only maybe 1 element, okay. So that is the idea, and this is the variation of bending moment, okay. And this is again I am showing at what point I am plotting this, the variation of curvature along the length, okay. So that is indicated by this. This is step number 105 of the solution. So I have 100 steps of lateral load and 5 steps of gravity load. So this total is 105, okay. So this is for the finer mesh. Let us compare this with the previous case when we had elements of equal length, okay. So let me show you that. So this is what we had for, let's take the case of 4 elements, right. So the green curve, let's look at this green curve versus the finer mesh. You see the difference. So this green curve is matching much better with the reference solution than if you use the element of equal length. You take any other example, let's say the case of 8 elements, okay. So 8 element is blue versus this blue here, you can feel the difference, right. So the conclusion I want to make is that for the same number of elements NLE, response is much better for this case when you are doing a finer discretization than equal length element. And this is the whole idea of finite element analysis, okay. This is for displacement based element, right, and the axial force along the length, okay. Now let us conclude that in force based element, you can improve the accuracy. There are 2 ways to increase it. One is by increasing the number of elements, the other one is by increasing the number of integration points, right. So number of elements or integration points, which one is preferred? Of course, increasing the number of integration points is preferred, because if you add 1 element, okay, you are adding 3 degrees of freedom. So let us say if I have 1 element and I am adding another element, so I have actually added 3 degrees of freedom, isn't it? Instead, if I increase the number of integration point, my computational effort does not increase so much. So therefore, in force-based element, we will use single element, more number of integration points. In displacement-based element, you can improve the accuracy by only one means, that is the increasing number of elements. Okay. Of course, you have to use a minimum number of integration points, otherwise you cannot get the solution. So accuracy cannot be improved by increasing number of integration points beyond a minimum required. So use finer mesh only in the plastic hinge region, right. So for more details on this, Neuenhofer and Filippo has done a study, okay, using a nonlinear beam column element which looks like this for 3D, okay, and then they have applied some load on it. Okay. So I have just taken a cantilever for the sake of simplicity, because it is a statically determinate system. So I know the solution when it is linear elastic. Also it is easy to see. Okay. Now let us talk about what happens for the same example when the material behavior is elastic perfectly plastic. If you recall, we are talking about three different responses. So let us say H versus delta. One is like this, which is strain hardening. The other one is like this, which is EPP, right. And then there is another one which is we are calling strain softening. So this is softening. Okay. So we have discussed the strain hardening. Now let us see what happens if the material behavior is elastic perfectly plastic. So what I will do, I will change that alpha, the strain hardening ratio, to a very, very small value and redo the examples. Okay. Again, so this example is also shared with you. This is the same example 3, but modified. How I am modifying it? Everything same. So this is my cantilever. Okay. I am using only one force-based element, but I am now using elastic perfectly plastic material behavior. So this is my sigma epsilon response. Earlier, I had a strain hardening ratio of alpha is equal to 0.005. Okay. Now, I am not giving any reference solution for a reason that you will see in just a little bit. So, as I did earlier, I was increasing the number of integration points and studying the convergence of solution, the global response and the local response. So, as you can see, the global response, that is the axial force versus vertical displacement for the cantilever, and lateral force versus horizontal displacement, both are converging with the increasing number of integration points, even if the material is elastic perfectly plastic. Okay. What happens to the local response? Okay. This is where it becomes interesting. So, we are looking at the curvature again at different sections. Okay. How many sections we have? For 3, we have 3 sections. For 9, we have 9 sections. So, what do we see? The bottommost section, because I am using Lobato, so I have an integration point at the element end. So, for the bottommost section, what do we see? The curvature values are different for different number of integration points. Okay. Here it is fine, but here they are different. So, global response converge, I get an objective solution, but the curvature, the peak value of curvature at the base is varying as I change the number of integration points. In other words, I am not getting a converged solution. In other words, we call it loss of objectivity. The solution is no longer objective. Okay. The moment variation is fine, but only problem is with the curvature for elastic perfectly plastic response. So, similar observation for the axial strain. You see at the base section, the axial strain is different for different number of integration points. The same example as before, only change that I made is I reduced that alpha value to extremely small value. That means the material behavior is elastic perfectly plastic. So, peak axial strain demand also varies with the number of integration points, again loss of objectivity. Okay. I also plotted the section force deformation response at the base. So, that means here is my cantilever subjected to axial load and lateral load. I am looking at this cross section and plotting the axial force and axial strain at that cross section and the bending moment and curvature at that cross section. Okay. What do you see? Well, they are matching quite well up to the yield. Then you see this is the maximum axial strain when I use 3 integration point. This is for 5, 7, 9. Similarly for curvature, this is for 3 integration points, 5, 7 and 9. So, what do you see? The peak curvature is not predicted in an objective manner. It depends on the number of integration points. So, I do not know what is the correct solution. So, the objectivity is lost. This is with force based element. I will also show for displacement based element what happens, but for the time being, for the force based element, when we have elastic perfectly plastic response, the global response converges, but the local response, the deformation response basically does not converge. It loses objectivity. Why does it happen? Let us try to understand that. So, let me first draw this cantilever. So, this is the cantilever where we have some axial force and some lateral load, right. So, we have applied the axial force and then we are applying the lateral load in a displacement control mode. We are increasing the lateral load slowly. So, when we increase the lateral load slowly, then what happens? My material response sigma epsilon is elastic perfectly plastic. So, what is my moment curvature response? The moment curvature response at any section is also elastic perfectly plastic, isn't it? Well, this is not exactly like this, but there will be a curve part because this is My and MP, this is MP, recall from previous lecture that MP by My I am using an I section is approximately 1.14, right. But once it reaches MP, it is flat, okay. But there will be a transition here, that is okay, right. So, if I keep pushing this using a displacement control mode, when the MP is reached, then what happens? The bending moment diagram, let us say, is like this, and this moment is MP, right. Now, if I keep pushing it, no matter how much I push, my material behavior is elastic perfectly plastic. So, the moment curvature is flat. So, moment cannot exceed. Okay. So, this remains MP, right, and the rest of the cantilever will remain linear elastic, has not reached MP. Okay. So, the lateral load carrying capacity of the cantilever is reached, the moment MP is developed at the base, right. Now, as the tip displacement is increased, I am applying more and more displacement. What should happen? The curvature of the base integration point increases with constant MP. Why? Because if you recall, for the force based element, I have derived this using principle of virtual work that the V, what is V? The deformation at the element ends, which is basically axial displacement theta I and theta j is equal to what? Integration B transpose x, then V bar x dx integrated over the length. So, what is this here? This is my vector of section deformation, which is epsilon x and psi x. So, what is psi x? Is my curvature. Now, let us talk about the curvature at the base of the cantilever. Okay. In this case, I am applying a lateral displacement. If I am applying lateral displacement, that will increase basically this rotation, okay, the chord rotation. So, as I impose more and more displacement, then what has to happen? This curvature has to increase at the base section. Why? Because all other cross sections along the length of the element remain elastic. Bending moment diagram is not changing. So, as the displacement is increased, you are pushing it like so, the curvature here has to increase at the constant moment, right. Okay. Now, length of the base integration point and consequently the plastic hinge length becomes a function of number of integration points used. What is meant by that? If you recall from before, So, we are integrating a function 0 to L fx dx. Okay. So, if we use this, I can write it -1 to +1 f in a normalized coordinate psi d psi, okay, which is approximately equal to L by 2 summation w I f psi I, okay, for I is equal to 1 to n. Okay. So, what is this w? Is the weight of each integration point. I is the 1 to n number of integration point. F psi is basically this function that we are integrating, isn't it? So, that means in the previous case what I wrote B transpose V bar x dx. So, B transpose V bar is that function that I am integrating, right. And if you recall from the previous lecture, summation of this integration weight is equal to 2, right. So, that 2 multiplied by L by 2 is basically the length of the element. So, that means if you actually work in the physical coordinates, so let us say I have this element, right. So, the sum of the integration weight in the physical coordinate, not in the psi coordinate, because psi varies between -1 to +1. The physical coordinate varies between 0 to L. So, this is 0 to L, right. So, the summation of the weights of the integration point is equal to the length of the element, right. So, that means if you increase the number of integration points, the weightage, let us say if I have 3 Gauss-Lobato, so these are my integration points, right. So, the weights are such that this, if you add them, you get the full cantilever. Let us say for this one, then this is that one, and then this is the weight, right. So, if I keep on discretizing it with more and more number of integration points, then what happens? My weight is reducing. Weight of one integration point is reducing. Now, remember at the bottom we have got maximum bending moment, right. If I keep pushing further, bending moment cannot increase, and that weightage of that integration point has reduced. So, that means in essence the length of the plastic hinge has also reduced, because all other sections are remaining linear elastic. Okay. That is what I am trying to say. Length of the base integration point and consequently the plastic hinge length becomes a function of number of IPs used. If you have less number of IP, the weightage is more and the length of plastic hinge is more. Okay. So, as the number of IP increases, the plastic hinge length decreases, and curvature demand in the base integration point must increase to yield the same prescribed tip displacement, because eventually you have to integrate this curvature and strain to get the element deformation. So, I am pushing the cantilever laterally. So, the curvature at the base has to increase, because that is the only section which is inelastic. All other sections are remaining linear elastic, right. And as I increase the number of integration point, that weightage is reducing, hence the curvature has to increase even further. So, that is where the loss of objectivity in the peak curvature is happening at the base section. Okay. Now, what happens if I use displacement based element instead? Okay. So, I took the same example that we did, example 5, and modified it by just changing the material model to EPP. So, this is the material model now. Everything else is remaining the same. Okay. And of course, I have removed the reference solution, because just like we have seen, there is a loss of objectivity at the section deformation level. So, I do not know what is the exact solution, hence I am keeping that away. Okay. So, you can see the global response, lateral force versus displacement with increasing number of elements for displacement based element tend to converge, which is okay, right. Here also it is tending to converge, the axial force versus vertical displacement, right. What happens at the section deformation level? Okay. So, this is curvature and this is plotting along the length of the element, and as we know before, the curvature varies linearly within an element. So, this black is the case of 16 elements. So, here is the bottommost element, then the rest. So, very interesting thing is going on here. You see, let us take the example of 16 element. Only one element is having a curvature of -0.61 by meter. All other elements are having pretty much 0 curvature. On the other hand, if I take 8 element case, only this bottom element is having a curvature little more than 0.31 by meter. all other elements are remaining linear elastic. So this is exactly what was happening in the force-based element, but over one integration point. Here it is happening over one element. So the localization of deformation cannot be avoided, whether you use force-based versus displacement-based. Here it is happening over one element, there it was happening over one integration point. Okay. So global response converges, it is objective, but peak curvature demand varies with the number of elements. Okay. Same observation for the axial strain. You can see when I use 16 element, this is my peak axial strain. When I use 8 element, this is my peak axial strain. There is a huge difference. For axial force, it's okay, right? So peak axial demand also varies with number of elements. Okay? And again, we lose the objectivity. So in summary, for elastic perfectly plastic response, the deformation localizes in one integration point for force-based element over one element for displacement-based element. So what happens for strain softening response? Remember, we talked about 3 cases. This is one, this is EPP, and this is the strain softening. So what happens for strain softening? Well, we shall see in the next lecture. So there we will lose objectivity for the global response as well. Okay, we shall see that. With that, let me summarize. So in this lecture, what we have done, we have looked at how you can get a converged solution for displacement-based element when the response is of strain hardening type. What you have to do? You have to increase the number of elements. Now, you should do it wisely, meaning that you should use more number of integration points where the plastic hinges are expected to form. Everywhere else, you can use longer elements and less number of elements. Okay. Loss of objectivity in predicting section deformations can happen in both force-based element as well as displacement-based elements. None of them are free from this problem. Okay. We discussed only EPP. In the next class, we will talk about softening response, strain softening response, and we shall also see there are many ways that researchers have developed. We shall see one of the ways to mitigate this problem. Okay. So in this lecture, I have used this reference which has a similar study like what I showed you using a cantilever. If you are interested, please go ahead and take a look. They have used a 3D element, and also they have talked about a higher order displacement based element. Okay. With that, thank you and see you in the next lecture.